Hello everyone, this is Hsiao. I'm the PhD student from Department of Material Science and Engineering at National Cheng University. I'm going to serve as the moderator of Photocatalytic materials for dye degradation session. In the very beginning, I'd like to introduce our distinguished panelists today. First, we are very delighted to invite Dr. Joon Ching Juan, Associate Professor of Malaya University at Nanotechnology and Catalysis Research Center. And let us welcome Dr. Chia-Yun, Associate Professor of Department of Materials Science and Engineering at National Cheng University. The first presentation in this session will be presented by Dr. Joon Ching Huang. And his topic is highly photoactive of expanded and softer vacancy of MOS2 under visible light emitting diodes. Before the presentation, let me make a brief introduction. The treatment of water pollutants, especially organic dyes, have been considered the vital issues, but instead, the remaining problem. Among various potential solutions, the oxidative degradation of organic dyes under light illuminations is the most efficient and eco-friendly method. In this webinar, the photocatalytic material with low cost, high absorption, and recyclable capability for pollutants treatment will be introduced. Okay, I have finished the introduction. And Dr. Joon Ching Huang, you can start your presentation.
Thank you for the kind introductions. So without further delay, so I would like to start my presentations. So as mentioned, I will share with you the project or the research entitled Highly Photoactive Expanded and Sulfur Vacancy of MOS2 Under Visible Light Emitting Diode. Short form is the LED. Okay. And also I want to thank the Cheng Universities and NCKU office in Vietnam for inviting me to share this project. And this project is a collaboration with NCKU under Professor Chia-Yun. Okay. So this is my brief what I call biography of myself. So I'm an associate professor in University of Malaya. Of course, my research area, you can see, is focused on the nanomaterial to be applied in the environment. For example, today I will share with you this is the wastewater treatments, but also involved in others type of research in energy, environments, so for example, CO2 and VOC treatments, chemicals, and other type of research area using the nanomaterial. Okay. This agenda or the content of my presentations. So basically, as everyone know about the issue of water pollutions, right? Okay. So the textile industry is contribute about 20% of the wastewater from the textile industry, right? And this is what we can gather that is 7,000 tons of dye is produced annually. That means 1 year, 7,000 tons of dye is produced, and it generates massive amount of dye waste water, right? And you can see from the next picture, 15 to 20% of the dye used was discharged right into the environment. Okay, so this is the issue that we need to tackle under UN SDG goal, right? Under the number 6, we should provide a clean water and sanitations. And by using this technology, right, we will like to reduce the effect of the wastewater pollutions in human health, in aquatic ecosystem, and also in plants. So this is technology that have been used so far. First is the technology on the treatment on the using the anaerobic digestions. Okay, so what is anaerobic digestion? Basically, they are using a microorganism or bacteria to treat the wastewater. So of course, their advantages is produce a renewable energy, but they have their own disadvantages. For example, they have a very slow process, and the conditions, right, okay, changing, okay, because you are using bacteria, it produces a lot of ammonia, which is toxic, and changes of the environment will also deactivate or denature the bacteria easily. So this is the advantages. Absorption is one of the most common method to treat wastewater, right? Okay, it's simple and can handle in the micro level pollutants. That's why it's a very mature technology. However, right, these adsorbents, if you look at the adsorbent, need to change regularly because it's very fast. It will be contaminated or absorb large amount of pollutants, right? And then after the lifetime of these adsorbents, they need to discharge, so they produce a secondary pollutants. That means the adsorbent itself become a pollutants. Okay, so of course we are very famous membrane technologies, and a lot of research is being done. This is very good technology, low cost, a low operating and maintenance cost. Again, the due to massive amount of pollutants, this easily clog or block the pore of this membrane. Okay, and then also form the cake layer. It form a massive cake layer on the surface of the membranes. So this is the issue they are trying to tackle for the membrane technology. Of course, we have some for microbial fuel cell. That means we're using bacteria to treat the wastewater. At the same time, we generate electricity. So low construction and operating costs, but this do not suitable for large applications. It's still in the research stage, right? Okay, because the proof of this bacteria and also the technology is not matured. So we are talking about this photocatalysis or advanced oxidation process in very important. This is very good because cost effective, no secondary pollutants generated. Very simple process. You just use your photocatalyst and some sunlight. You can destruct the organic pollutant. That means you what we call the destructions. You destroy the organic pollutants under the sunlight. It means basically sunlight you generate the radical, and this radical will degrade the organic pollutants, so do not generate any secondary pollutions. So there are three main steps. I don't want to go in details, but basically by sunlight they activate the photocatalyst. The electron jump into the conduction band and leave a hole, and if the water attached to it, it became a radical, and this radical is going to attack or destroy the organic pollutant. Same go in the conduction band, which is have the electrons here. The oxygens dissolve oxygen in the water, becomes superoxide and attack the organic pollutants. So it destroy the organic pollutant to CO2 and water. So what we're going to focus today is the use of this called MOS2, molybdenum sulfide. Okay, so this is known as a co-catalyst for a long time, but we discovered that MOS2 itself can be the photocatalyst. We can tune the band gap of MOS2 to make it as a catalyst instead of a co-catalyst. Because by itself, the MOS2 have a band gap of 1.2 eV. So it's not very suitable to become a photocatalyst because recombination is very fast. So they cannot generate the radical that I mentioned just now. Okay, but using our method, we try to tune or engineer this interlayer spacing. We increase or enhance this interlayer spacing to 1.98 eV, for example, if possible, right? If we can increase to 1.6 and above, also consider good. Then we can activate this ammonium sulfide, become a photocatalyst. This is what I'm trying to say. The band gap 1.2, so it's not suitable. But if you increase this band gap to 1.6 to 1.9, then it will be a suitable photocatalyst that can be activated under visible light. Okay, so this is our target. Okay, so we're going to engineer or tune the 0.62 interlayer spacing to more than 0.62. Okay, to get this band gap value. So what our strategy, right? Okay, we have to understand the structures of this MOS2 before we able to tune or to engineer this MOS2. So this is a structure of MOS2 is a layer structures. So this layer we want to expand it. MO atoms are located in the betweens. Okay, you can see MOS2. Okay, one molybdenum. You have 2 sulfur. Okay, this is the 3D structures of the MOS2. They have a H planar and a basal plane. Okay, so the interlayer is bonded by van der Waals force. This layer, okay, is a very weak van der Waals force. Okay, so we need to expand it. Okay. Due to weak van der Waals, interlayers can be expanded by introducing a surfactants, the ions or carbon or etc., or some simple methods of sonications, right, to expand this layer. So we must have a suitable energy to expand this layer. If we put excessive force, the interlayer will be peel off, just like a graphene. Okay, if you peel off, it become a single layer. So this one we do not want to have that because we want to keep the interlayer. So we have that particular band gap. So this is our challenge. So after the discussion and experimental, we're going to use a surfactant to increase the interlayer spacing. So this is our strategy. Okay, so we of course this is a material to make the MOS2. So we introduce a surfactant F124, a non-ionic surfactants, treat under the hydrothermals, okay, 24 hours, and then we wash, of course, again, then we dry in the oven. Then we test our photo activities under 1 watt of LED white light, okay, because we want to give some challenge to it, because if you use these 150 watt xenon lamp, is a high intensity. So we want to use a low intensity, low wattage to test this photocatalyst. So this is the spectrum of the LED light. Is most of time is in the visible region only, more than 400 nanometer. So this is the XRD that we managed to obtain. This is a pristine MOS2 0.62. Okay, so we successfully synthesized MOS2 as a standard because it's based on literature is also 0.62. Then we introduce these surfactants. Okay, by introducing the surfactants, yes, we managed to increase the interlayer spacing. Okay, from 0.62 to 1. Okay, and then we tune the pH because the pH is very important. By tuning the pH, we can alter the interlayer spacing because we protonate the non-ionic surfactants and also the molybdenum ions. So by tuning to pH 1, we can manage to get 1.51 interlayer spacing. Okay, and this can be proved from the XRD patterns. So then we can look at the SCM. So look at the pristine MOS2 is a very nice coral-like shape. Okay, so when we introduce the surfactants, is also remain as a coral-like shape, but a bit nicely separated as compared to here is big chunk or clump. Okay, by induced surfactant, it seems that it's loosened a bit because the layer is a good dispersing agent. Okay, then we decrease the pH. We make it more acidic in that sense, so that you can see things keep changing. Okay, the morphology of coral becomes slowly separated. The layer becomes separated, and the extreme pH 1 have been separated dramatically. So from there, you can see this issue of F124 is protonated, creating an electrostatic interaction with the molybdenum ions. This inhibits the cell's assembly process. Thus, a random distribution of MOS2 plate structures to form the MS1. So that's why you can see the interlayer spacing and the rearrangements of the MOS2. We also look at the TEM image. So you can see the pristine MOS2. The layer is about 20. Okay. By introducing a surfactant, it becomes 10. By increase the the pH, decrease the pH. Sorry, again, decrease the pH to pH 1. We get the layer is become decreased to 6. Okay, because it's keep peeling off some of them. Okay, the big chunk is peeling off because I think it's a very weak van der Waals force, so it keep peeling off in that sense. So you can see that the thing is losing up, then give a vertical number of defect structures. Also, we observe some defect structures here. Okay, So this defect structure is a good thing because it's exposed to the active site of the MS1. So it's a potential for the photocatalyst organic pollutant degradations. So we also observe from the Raman, okay, you can see the shifted, okay, the MOS2, the pristine MOS2 have shifted, okay, these two have shifted. So that means the MFF has smaller number of stacking layer and confirmed by the HRTM. So then TM and Raman have a concordant result. Then we go to the UVs, okay, we look at the band gap. Okay, so the band gap is just nicely done. Okay, so we in our range 1.91 to 2.006 EV. So this is also proof that we managed to get the range that we want. So we can conduct this experiment under the what we call visible light. So we also done the SPS analysis because we want to see the MOS2 structures or the oxidation state, any changes on the oxidation state or not. Fortunately, we found that the thing really changed. Sometimes changes is good, right? Okay, the sample M, okay, 2.0, okay, M do not have this ratio because all is MOS2, okay. Basically, but after the introduction of these surfactants, the oxidation state changes, okay, and then it do not have normally one MO, two S2, it's called MO S2. So one molybdenum atoms will be having two sulfur, okay, but by introducing the surfactant, it seems that we have some called the sulfur vacancy, okay. You can see the sulfur vacancy here. So you can see the is decreasing, okay, to 1.5. That means the sulfur vacancy formed, okay. Forming the sulfur vacancy is a good thing for us, okay. This one you can see the sulfur vacancy enhance the exposure of the sulfur surface of the molecular active site, okay. So the absorption energy for O2 molecule from the environments, and also promote the migrations of the electron to absorb more O2 to form the superoxide radical. Okay. So then we run our photo activities under the LED light. Okay. So we can see that the photo activity, okay, for the MS1 is very good as compared to others catalysts. Okay. For example, compared to the pristine MOS2 is tremendously 3 times, at least 3 times better. The photoactive is 3 times better. Okay, so that means we have increased the interaction, increased the exposure of the active edge site, and promote the sulfur vacancy, promote the in situ generation of reactive oxygen radical. Okay, and so we also test the radical. Okay, we also correct concordant with our theory. The dominant species is the superoxide from the promoted by the sulfur vacancy, and we run the reusability. It seems very good, high reusability. After 5 times using it, we don't see any significant reductions on the photo degradations. This is the conclusions, right? So that we can see this what happened to the what I call our photo catalyst. And this work have been published together with Professor Chia-Yun. Okay, we published in the Nano Scale Advance. For more details, you can look at this paper. So this is what happenings by having the sulfur vacancy and the interlayer spacing. This can be activated under the visible light. Okay, and we found that the O2, mean the superoxide, is the main radical that degrade the dye, okay, to CO2 and H2O. Okay. So of course we also compare with others people's experiments and so on in terms of two things. One is the interlayer spacing. Okay, you can see from here we managed to produce the largest interlayer spacing. Okay, and this of course is not applied in the photo activity. Okay, it implied mostly in the battery. Okay, in the battery. So you can see in battery for electrochemical and so on. Okay, For this work, we managed to 1.5. So it may be can be applied in the other field. Okay, for example, battery especially. And we compare the MOS2 as well. Okay, for other research, and you can see from here, all using very high intensity light source. And we are the first one using 1 watt of LED light only. Okay, you compare to here, it's like, for example, it's 100 times less energy. Okay, we are degrading the same dye here. Okay, and same concentrations, about same concentrations, 10, but we are using 20, 2 times better. Okay, and we managed to get about 98% degradations in the shorter time. So it's 150 minutes, it's 120 minutes. Okay, from this work. So this is the end of my presentations. This is the reference, and also want to invite those are interested to submit in the my special issue. One is the nanomaterials with the impact factor 4.3 Q1. The submission deadline is 31st January 2022. Okay, and second one is the Belston's Journal of Nanotechnologies. Okay, so impact factor 2.2. So I invite all interested party to submit this to this journal. Thank you very much. Thank you.
Okay. Can you hear me?
Yes, yes.
Okay. Thank you very much, Dr. Ching for your excellent presentation. And now we'll proceed to the question and answer session. Is there any question here? Okay. I think I have some question. Yeah. First, I want to understand, is this method can make a monolayer or bilayer MOS2 from change the pH, maybe more sour or what?
Actually, very good questions. You can see the pH have been what you call adjust to the maximum level, pH 1. So at this point, of course, you can put more acid, right? But you cannot measure the pH anymore in that sense.
Okay.
I mean, it can be a pH 0.1, but our pH meter not able to manage to evaluate this pH. You have to use another method. Okay.
Okay.
To prove of the concept, of course, you just use pH 1. But I think, based on my experience, you can adjust the acidity, okay, to extremes. Then you might able to form, okay, what we call different type of substrate, as you mentioned, bilayer or tri-layer and so on. Because as the acid is going to extremes, I believe the protonation will also increase. But of course, it will reach a limit. You cannot reach a limit. That means then it will not able to what we call protonate the molybdenum anymore. Okay, and the second thing you can do is increase the concentration of the surfactants. Okay, to a optimum point. Then only you adjust the pH, because when you increase the amount of surfactants, right? That means more surfactant is going to disassemble, okay, or disturb the molybdenum sulfate doing the arrangements. So it will form very small type, four small MOS2. Okay, it's not very nice. Maybe the plane will not be that flat, for example, right? If under normal condition, it will be a flat, long range type of MOS2. But you can do more than that, right? Going to extremes, maybe the thing is become smaller, or just a 2-layer or single layer. If you go to extreme, maybe the van der force is disturbed, so you maybe have a single layer. But I don't think you get a single layer, because it still form the layer to get the MOS2. That's the beauty of surfactant that we think is suitable. Other method, it will disintegrate the layer. That means you just peel off the layer. This is the thing that we trying to avoid, because you don't have the photo activities. If you remove the layer totally, it becomes a single layer. That's the issue. It's good for battery. If you are looking at the battery, for myself, I'm looking at battery. That means it's good, because a single layer, the conductivity is very good for a battery.
Yeah.
For photo activities, for photocatalyst, it's not a good thing.
Okay.
You need to have the layer to have that band gap.
Yeah, I see.
The band gap.
Okay, and there's the other questions from the audience. What is the cost of the method compared to other convenient pollutants treatment methods? is it competitive when it comes to commercialization?
For commercialization, to be frank, you cannot just depend on one method to treat wastewater. That means you say, oh, membrane is very good. I just use a membrane to treat my wastewater, industrial wastewater. Okay, it will not be possible. You must have a separate step. First is the biologic treatments, right? Followed by the maybe the membrane. Membrane normally is the last because it's very expensive. Okay, so it will normally biological. Then you have the coagulant flocculants. Then only you have a membrane. That's the normal procedure for wastewater treatments. Okay, that means because we want to reduce the use of coagulant flocculant because it produce a lot of slush and use a lot of chemical. So before that, after biological treatments, so normally we need to apply. That means we can apply this photocatalyst. Okay, so we'll degrade a number of the organic pollutants, right? So first, maybe you not need to use any coagulant flocculant anymore, or you can reduce the amount of coagulant flocculant. So you can reduce the amount of secondary pollutants because you use slush, you use a coagulant flocculant, you form a slush. Okay, a cake, like a cake, a slush, okay? After you press into a cake, right? Okay, you form a secondary pollutant and uses chemical. But you can reduce half or even 30%. Is good enough for the environment because we are not talking about 1 kg, not talking about 10 kg. We talk about every day is 1,000 tons, okay, of wastewater or industrial wastewater is dumped into the environment. So this is the thing that we're trying to tackle.
Okay. And there's the second question. Hydroxyl radicals are the main factor to proceeding the active pollutants degradation. Is there any way to create more and more hydroxyl radicals?
Yeah. So two things about photocatalysis. One is the hydroxyl radical. One also the superoxide radical. Okay, hydroxyl radical is the unpaired electron of OH. Okay, superoxide radical is oxygen with the unpaired electrons. So these two type of radicals is the main what I call main criteria or main radical that degrade the organic pollutants. So to produce these two radicals, right, you need to reduce the electron recombinations. Okay, because once a electron is promoted from a valence band to a conduction band, okay, it will tend to go back to the what you call the valence band quickly, very quick pop. Talking about maybe femtosecond, okay, they go down. So you must slow down this recombination. That means don't let the electron from the valence band go down fast enough. Okay, so we have to retard, sometimes because it retard or suppress the electrons recombinations. Then you have a time to produce more radicals. For my case, we produce the superoxide radical, okay, O2 radical. So we produce this called sulfur vacancy. We discovered that sulfur vacancy, right, can suppress this type of work. And then we produce more superoxide radical to degrade the organic dye. That's why you can see the activities increase tremendously. And superoxide radical actually is more active than the hydroxyl radical. That's why you can see the usability is always very good. Because it's just oxidations are very strong. They just degrade all the organic pollutants. So our surface is quite clean in that sense. Clean means less things stick on it because it's so active. So everything is cleaned up. So that's why it can be reduced. You see, if not, then the thing is stick on our surface, the photocatalyst surface. Then the usability reduce. So we need to take care of that as well.
Okay. Okay, thank you for the clearly explanation. And let's start the second presentation. Okay.
Thank you very much. Thank you for
okay, sorry. Okay, the second presentation is the session will be presented by Dr. Chia-Yun with the topic of pollutants treatment with silicon waste, photo degradation of dyes. Okay, before that, I make a brief introduction. The heterostructure-based photocatalyst with the superior capability for separation of photogenerations carriers has been considered the promising candidate for the realization of high efficient and reliable photocatalyst system on the removal of organic dyes. Various potential heterostructure-based photocatalysts will be introduced in this webinar. And Professor Chen Chia-Yun, you can start
Can you see my slides?
Yes, we can hear your voice.
But can you see my slide? No?
Oh, no, we can.
Okay. Okay, I have some issues. Can you wait for me a few minutes to change my computer?
Okay.
Just now we can see your slide.
Oh, yeah, but
Can you see my
Yeah,
slide?
we can see your slide.
it's okay. Okay, we can see it.
So right now you can see my slide, right?
Yeah.
Okay, thank you. So I will start my presentations. Okay, so hello, this is Chen, assistant professor in the Department of Material Science and Engineering from National Cheng University in Taiwan. Okay, so following the very nice talk provided by Professor Joon, my topic is also related to the photocatalyst or the photo degradation of the dyes. Okay, and the materials that I am interested in is the silicon waste. Okay, so in the first slide, I'd like to talk about the reason that we study silicon function as a photocatalytic materials. Okay, so there are several advantages of using silicons. Okay, for example, silicon is quite abundant in the Earth's crust. Actually, it is the number 2 of the materials abundant in Earth's crust next to the oxygens. And we have quite a mature manufacturing technology on silicon-based materials and fabrications. For example, your laptop, your computer, and your cell phones, all these are made by the silicons. Okay, and one of the very interesting characteristics of silicons that their material properties are quite stable in ambient conditions because of the self-formed precipitation layers, which is silicon dioxide. So due to the existence of silicon dioxide, the silicon could be very stable under a wide range of temperatures, humidities, and different atmospheric conditions. Okay, but when we try to apply the silicon for some specific application, like for the solar cells as examples, even we know that silicon is the most abundant materials for the fabrication of solar cells. So you can frequently observe the crystallized silicon solar cells in everywhere to generate electricities. Okay, actually, the market share of the silicon solar cell is more than 85 or 90% in the current renewable energy technologies. But in terms of their efficiency, it's not very good. Why? Because silicon actually itself is an indirect bandgap materials. So indirect bandgap materials means that once we are trying to convert the electrons, once we try to convert the photons to the electrons and hole pairs, for the silicon, in addition to apply enough solar energies, we require additional momentum change in order to count out the conversions of the photons to the electron and hole pairs. Okay, so due to such indirect bandgap features, the conversion efficiency of the silicon is very, very poor. Okay, this is one of the major limitations why that silicon could be not functioning as a high efficient solar cells. Okay, in addition, silicon has a very high reflectivity in the visible frequency regions. Typically, in the solar illuminations, the reflectivity of silicon is above 40%. Okay, which means more than 1/3 of the light, incoming light, cannot enter the silicon for generate the electron and the hole pairs. Okay, so these two issues should be overcome in order to use silicon as a photocatalyst materials. Okay, and talk about some practical issues. As I mentioned, the silicon, crystalline silicon solar cell is the most important materials for the current commercial solar cells, right? But let's see, after 20 or 30 years, okay, the efficiency of this silicon solar cell will be not good enough to generate electricity, which means we have to replace those silicon waste with new solar cells. So how can we deal with those silicon waste turn out to be very critical issues? So according to the concept of the circular economy, okay, we have to try to reuse or reactivate these used materials to other applications. So my idea is that we are trying to use those silicon waste function as the photocatalytic materials in order to treat the pollutant of wastewaters. Okay, so let me briefly talk about the ideas of photocatalysis. Actually, Professor Joon just gave a very nice explanation of the working principle of photocatalysis. So that's right here. I just give a brief introductions. So since we need semiconductor materials as a photocatalyst, so the semiconductor owns the valence and conduction band. So when the light illuminates these photocatalytic materials, the electron and hole will be generated. Okay, so there are two important radicals that will be created, including the hydroxy radicals and also superoxide radicals. And these kinds of radicals is quite oxidative, so they can quickly degrade organic dyes or organic pollutant into the harmless carbon dioxide and hydrogen and water. Okay, this is what we prefer to convert the harmful materials into the harmless species. However, for typical semiconductor photocatalysts, this efficiency is not good enough. Let's take silicon as an example. As I mentioned in the previous slide, silicon could not efficiently absorb the visible light or sunlight because of their high reflectivity. And in addition, silicon has a poor conversion efficiency. So to overcome these two domain issues, first of all, we have to improve the light absorption property of the silicons. And second, we have to introduce some heterostructures into with the silicon to incorporate the composite photocatalyst. The reason is that we could create a heterojunction between these two materials, and the heterojunctions with a proper design of a band structures, we could actually separate the electron and hole pairs prior to the recombination of the charges. Okay, to summarize, there are two critical issues to apply silicon function as a photocatalyst. The first issue is that we have to improve the capabilities of light absorptions of the silicons. And second, we need to establish, build up the heterojunctions. This is the one very important design or strategies in order to reduce the charge recombinations and generate more radicals to degrade the organic pollutant. Okay, so the first issue, how can we make the silicon become highly absorptive in the visible frequency regions? The ideas or some theoretical work have shown the way to do this. Okay, from here we can see some of the calculations, including effective material theories, to show that once we can change the morphologies of silicon into the nanostructures, especially the one-dimensional nanowires, according to these calculations, you can observe that the reflective index of nanowires could be reduced compared with the bulk silicons. So that according to these calculations, we can see that the reflective index of the nanowires is lower than the silicons, which means the light reflection from the interface could be significantly reduced. Okay, so this is the first reason that we want to convert the morphology of silicon into the nanowires. And second issues you can understood by these illustrations. It shows that once we can count out the nanowire arrays, then the incoming light shown in these red arrows will multiple scattered inside the spacing between the nanowires, which means we could generate more chance of light absorption at interfaces. And due to this multiple scattering of light, the the reflectivities of light onto the nanowires could be substantially reduced. As you can see, the left figure shows the reflectivity of the bulk silicons is average reflectivity is above 35%. But once we introduce a nanowire onto the silicon surface, then the average reflectivity can be reduced less than 3%. Okay, so this is an efficient way to improve the absorption capabilities of the silicons. But how can we do this? Okay, there are several ways to synthesize the silicon nanostructures, but some of these processes require high temperatures, vacuum conditions, and also the impurity contaminations, making the process cannot be applicable for the practical applications. So what we actually try to use is based on the wet etching process. As you can see, compared with a typical wet etch and dry etching process, our method can come out the nanowire arrays with several advantages, including the maskless, temper-free, large area, and single crystalline natures. And the whole process can be operated at room temperatures. So this is based on a very simple galvanic reaction between the silicon and the metal ions, such as silvers. Due to these galvanic reactions, the silicon will be oxidized, and the hydrogen fluoride can use to remove the oxide silicons. So this cycling process, including oxidation and dissolution, will occur many times, eventually come out these nanowire arrays at room temperatures. Okay, so based on this process, we have spent several years on this process. So currently, we are able to, in addition to control the width or dimension of nanowires, we are also trying to control the orientation. So such as very spatial slanted or zigzag shaped nanowires could be come out based on this mixed etching process. So this process could be used for the large area fabrication. So it's not only useful for the photocatalyst, but also can use for the solar cells or other microelectronic devices. Okay, so let me go back to the topic, the photocatalyst. So I would like to show 3 examples to use silicon as a photocatalyst. The first example is that we are trying to combine the copper oxide, okay, with the silicons. The copper oxide actually is a direct band gap materials with the energy band gap around 2 to 2.2 electron volts, which belong to the visible focus regions. So copper oxide actually is a very famous photocatalyst for the dye degradations. But unfortunately, when apply the carbon oxide as a photocatalyst, it inevitably causes the aggregations and morphological change during the photodegradation process. So for this kind of nanoparticles, we need special supporters in order to disperse the carbon oxide for the operations. They will make the photodegradation process more stable, right? So the idea is that we are trying to incorporate the nanowire, silicon nanowire with the carbon oxide. As you can see, the silicon nanowire owns a very large surface areas and one-dimensional natures. So this could be a very good supporters that used to disperse the carbon oxide. So right here you can see the morphology, and morphology shows that we are able to uniformly deposit the carbon oxide onto the wires. And from the reflectivity spectrum, you can see, according to the illustration shown here, the light will be multiple scattered inside the between the nanowires, and the carbon oxide can introduce the additional absorption of the visible light, so that the light reflectivity could be significantly reduced, showing this black line, okay, compared with the other case, okay. And the photoluminescence spectrum shows that the photoluminescence result will be suppressed. This is because that the heterojunction will be created between the carbon oxide and the silicons, so the charge separations will be enhanced, so that the radiative combination of the electron hole pairs will be suppressed, as evidence in these PL spectra. So based on this design and also the structures modifications, the photodegradation result could be improved as shown in these pink lines. Okay, so based on this, after 18 minutes, the you can see the color of the dye solutions will be significantly reduced, become more transparent, which means the dyes will be efficiently degraded and removed. Okay. So this is the second example that we try to replace the carbon oxide with the zinc oxide. Okay, zinc oxide actually is also a very famous photocatalyst. And the reason to do this is that zinc oxide has a wide bandgap natures with a bandgap energy around 3.4 electron volts, which means zinc oxide could be used to efficiently absorb UV light. So once we are able to incorporate the zinc oxide with the silicon nanowires, so this kind of composite photocatalyst could be a wide wavelength range photocatalyst. They can use to utilize the visible and UV light simultaneously to serve as a photocatalyst or to proceed the photodegradation process. Okay, but the problem is that how can we uniformly deposit zinc oxide with the silicon nanowires? So a very unique technology called the pressure-induced deposition will be applied in order to uniformly deposit the zinc oxide nanoparticles onto the silicon nanowires. Okay, in general, the process is applied by placing a slice of glass onto the nanowire surface, and the zinc precursor will be dropped into the nanowires, and then the heat treatment will be applied. So based on this, we can prevent from the aggregation of zinc oxide nanoparticle on the top surface of silicon nanowires and come out this uniform structures. Okay, so based on this design, we can actually observe the two advantage of this incorporated photocatalyst. First advantage that you can see the photocurrent enhancement compared with the bare silicons and zinc oxide incorporated silicon nanowires. You can see for the second case, we have better photocurrent enhancement. This is because zinc oxide can additionally absorb the UV light. So that's from the wide spatial comparisons in different wavelengths. These kinds of structures provide a larger photocurrent enhancement compared with the source silicon nanowires. And second, we can see the Venn diagram of the incorporation of zinc oxide with the silicons. Okay, as you can see that from these Venn diagrams, okay, the band bending occurred, so the Fermi energies between the zinc oxide and silicon will be balanced. And from these band structures, the electron, the holes from the silicon can be transferred to the intermediate band state of the zinc oxide. And also the electrons from zinc oxide will be transferred to the silicons. So the charges could be efficiently separated from the structures. Okay, in that case, we can use this idea to reduce the possibility of the charge accumulations. Since we have a lot of nanoparticles under the silicon, so we can see the charge transfer efficiency could be improved because there is a short distance for the charge separations. So this is also the reason that we have the higher photocurrent enhancement compared with the source silicons. And the photodegradation result also confirm that their degradation efficiency could be greatly improved. Okay, and the final example is that as I mentioned in the first part, the motivations of our research try to turn the silicon waste into photocatalytic materials. So we are trying to simplify the fabrication process. So in the third examples, we are trying to use the carbon nanodot. One of the ideas that for incorporating the carbon nanodot to the silicon is quite simple. The very simple drop coating process can be used in order to combine the carbon nanodot with the silicon waste. Okay, and second reason is that carbon quantum dot actually is a fluorescent materials. As you can see that from the PO spectrums, their emission wavelength is around 500 nanometers. So that once we are able to combine the carbon quantum dot with the silicon nanowires, so you can image that they are dual light source will be excited. The one light source is from the incoming solar light, And second light source is from the photo emissions from the carbon dot. This is the light with wavelength of the 500 nanometers. So this multi-driven light source, okay, from either the external illumination light or the self-driven luminescent light, they can simultaneously generate more carriers in order to proceed the photodegradation process. Okay, so that we can, from the photodegradation test, based on the adjusting amount of carbonyl dot to the sequence, the photodegradation results will be greatly improved under the visible illuminations. And reliability is also very good. Actually, during these cycles, they still maintain a very sound photodegradation capabilities. Okay, so here are some of the collaborative publications between us and Professor Joon. Okay, in this year we have 3 collaborative publications based on this project. Okay, so anyway, I would like to thank you for your attention, and we are working on try to converting the waste materials to the applicable applications. Okay, thank you for your attention. Okay, can you say again what is the questions? Sorry, I cannot hear your voice.
Hello. Do you hear me?
Yeah, right now I can hear your voice.
Okay.
Say again.
Because I clicked the muted buttons, but it didn't work. Okay. Can you explain clearly the oxidative degradation of organic dyes under light illuminations?
Okay. So according to the slide I just showed, okay. So when the light emits on the photocatalyst, the electron and the hole could be generated if the energy of the light source is larger than the band gap of semiconductors, right? So the electron and holes that can interact with the water and oxygens and generate the hydroxy radicals and the superoxide radicals. And these 2 kinds of radicals are very oxidative, which means they will very easily interact with the pollutant, especially organic pollutant, and then convert that into the carbon dioxide and waters. Okay, so basically the photocatalyst actually is a materials that can use to absorb the light and generate the radicals that can use to remove or degrade the pollutant waste. Okay.
Okay. The second question is, what are the limitations of this method and how to overcome them?
Okay, the limitation, I think for the, I guess you are trying to ask the commercial product is possible or not. Actually, to make the commercial product, the price is very important issues. Okay, so you can see in my studies, we are trying to use a very simple method. For example, we don't require the vacuum system or very elegant equipment. We just use the wet process or solution process to prepare our samples, and so that the price of the fabrication could be reduced. But for the practical applications, we still need to try to make the materials more reliable and stable for any kinds of environment. For example, the water treatment could be maybe sometimes it's different from case by case, right? For example, you are treating the industrial wastewaters, or you are treating some of the wastewater from the living source. So that we need to make sure that this kind of photocatalyst can be used for different wastewaters. Okay, so make the materials more reliable and stable for the degradation of dyes will be the key to realize the commercial product.
Okay.
Okay.
I think due to the time, so we have to. Okay, this is the final question. Do the density of ZNO silicon heterostructure nanowires affect the results?
Sorry, can you say again?
Do the density of ZNO-Si nanowires affect the results?
Zinc oxide or something?
The density of zinc oxide.
The density of zinc
nanowire.
oxide. Yes, actually, the density of the zinc oxide will be very critical. Okay, so that we trying to change the synthetic process because we have to prevent from aggregation of zinc oxide, which means the density of zinc oxide cannot be too large, or the aggregation will be occurred. If the aggregation of zinc oxide occurred, then the photodegradation efficiency will be decreased. Okay, and so that the density cannot be too high. Also, the density cannot be too low. Once the density is too low, then the charge transfer pathway will be reduced, right? The number of charge transfer pathway will be reduced. Then the efficiency will be also reduced. So that we need to adjust the optimum density of zinc oxide nanoparticle onto the silicon nanowires to come out the better photodegradation efficiency.
Okay. Thank you for the completely explanations. And we have finished all the presentations today. And thank you